Hello everyone. I call myself Mr. U.S. Patil, working as assistant professor at Sharad Institute of Technology, College of Engineering at Rao, Ichalkarji, Kolhapur district, Maharashtra. So we are going through a B-Spline curve in a CAD. So most of shape are simply too complicated to define using a simple Bezier curve as we have previously gone through. A spline curve is a sequence of curve segments that are connected together to form a single continuous curve. If you say an example of a piecewise collection, a Bezier curve, connected end to end, can be called a spline curve. So before moving to B-spline curve, we'll go through some brief about a Bezier curve. That Bezier curve has some equation that polynomial degree of n. The from the software point of view, the data base of Bezier curve includes the coordinates of the control points, defining its polygon stored in the some order as input by the user. The other information which may obviously be stored include layer, color, name, font, line, width of the curve, etc. While a Bezier curve seems superior to the cubic spline curve, there is no doubt in that, but it still has some disadvantages. If you see mm, here, the curve does not passes through a control point. The first disadvantage is that the curve does not passes through the control point, which may be inconvenient to the some designers. So second one is, we can say, the curve lacks a local control. It only has the global control nature. It doesn't have local control. It has a global nature, that control nature. If one control point is changed, whole curve will be get changed. If you see here, this is initial curve of point P0, P1, P2, P3, and the curve is this. If the point P2 is placed at P2 star, the entire curve has been changed as previously this, and hence P2 has changed to P2 star, so automatically entire curve has been changed in this manner. So it called a total entire changing this curve is called global control nature. So we know that this is the polynomial degree of definition of Bezier curve, that P of u equal to sum of n I equal to 0, pi bi n of u. If say equation number 1, here P of u is any point on the curve, so this is any point on this curve, and P is the control point, that is P0, 1, 2, 3, and bi and r is the Burstone polynomial that we have gone through. Now these are the two disadvantages of Bezier curve. Now if you see in a B-spline curve, the B-spline curve provides an effective method beside the Bezier of generating curves defined by polygons. In fact, uh, the B-spline curves are the proper and powerful generalization of Bezier curves. In addition to sharing most of the characteristics of Bezier curves, they enjoy some other unique techniques, unique advantages as well. They provide local control of the curve shape uh, and opposed to the global control by using a special set of blending functions that provides local influence. They also provide the ability to add control points without increasing the degree of the curve. The B-spline curves have ability to interpolate or approximate a set of a given data points. Interpolation is useful in the displaying design or engineering results such as the stress or displacement distribution in the part, while approximation is good to design free form curves. Interpolation is also useful if designer has a major data points in hand that must lie on the resulting curve. In a contrast of Bezier curve, the theory of B-spline curve separates the degree of the resulting curve from the number of given control points. While four control points can always produce a cubic Bezier curve, they can generate a linear, quadratic, cubic, or B-spline curve. This flexibility in the designer uh, in this flexibility in the degree of the resulting curve is achieved by the choosing the basis or a blending function of B-spline curves with an additional degree of the freedom that does not exist in the Boston polynomial or Bezier curve. These basis functions are the B-splines, thus the name called as B-spline curves. So similar to Bezier curve, B-spline curve defined by n plus 1 control points, that Pi is given by a P of u, uh, sum of n I equal to 0 Pi ni k and of u. That equation 2, this is what a B-spline curve defined. If you see, Bezier curve is P of u, a sum of n I equal to 0 Pi bin of u. Here bin of u, and here if you see, this is what ni k of u. The ni k u are the B-spline functions. Thus B-spline curves have B-spline bases, the control points that sometimes called uh, D Boer points, from the vertices of the control. There are two major differences between these two Bezier curve definition and this spline. The parameter k controls the degree. Parameter k is controls the degree. K is just order. The polynomial equation has a degree that we call that k minus 1. That number k is a order. The number of points that you can say that k is an order. Of the resulting B-spline curve, and is usually independent of the number of the control points, and this is restricted in 2 and CP, that is K is less or equal to 2 and less than control point. CP means this is control points, right? So this is what a B-spline function Nik of u is a B-spline function. The properties of these B-spline functions are, the first you can say, first property ensures that the relationship between the curve and its defining control point is invariant under affine transmission. So here, second property uh, guarantees that the curve segment lies completely within the convex hull of Pi, that is point control points. Convex hull is nothing but this is a dotted line is called the convex hull, and it lies here only within that convex hull, under that convex hull. The third property indicates that each segment of a B-spline curve is influenced by only k. That I told that k is a order that of control points, or each control point affects only k curve segment, right? The k curve segment is nothing but a k is a order including a, you can say k equal to 1. 1 means considering 1 point, or k is 2 means considering 2 points. If you say k3 is equal to considering 3 points, including 3 points, you creating one segment. And if you say k equal to 4, so including 4, you can create a 4 segments, like that, so on. So here, it is useful to notice that the Beston polynomial bi and u has the same two same as two property of that Bezier curve, right? So here, the B-spline functions also has the property of recursion. There is recursion means the act of the defining an object or function in terms of that object itself only, right? So if you see the characteristic of B-spline curve that are useful in the design can be summarized, right? The local control of the curve can be achieved by changing the position of a control points, using multiple control points by placing several points at the same location, or by choosing the different degree, that is k minus 1. As mentioned earlier, changing one control point affects only k segments, right? So figure here it shows the local control for a cubic B-spline curve by moving P3 to P3 star and P3 double star. The four curve segment surrounding P3 changes only. The four curve segment surrounding P3 changes only. If means if we see here, the red line is the curve before changing a P3 to P3 star or P3 double star. That is initial points. If you say that is P0, P1, P2, P3, P4, P5, P6, P7, these are the control points located, and the curve is generated as shown in the red color, right? So if I want to change this point P3 to P3 star, the curve has changed within that 2 to 4 only, means 2 3 4. The curve has been changed in the portion of segment only. So this is what a local movement control of B-spline curve, right? So similarly here, if you drag here, if you transfer P3 over here, so the curve up to the point 2 1 P1 here, it will be same. Only from P2 to P4 it would be change if you changing the P3 to P3 double star, right? So hence the segment between where you have changed, only that much area the curve has been changed. It won't change entirely, so it's called a local control. So now this is what a property of then. And another one is non-periodic B-spline curve passes through the first and last control points. That always it passes through first and the last control point. The increase in the degree of the curve tightens it. In general, the less the degree, the closer the curve gets to the control points. If you see figure this one, when a k equal to 1, a 0 degree curve results. K equal to 1, a 0 degree curve results. The curve has then becomes the control points themselves. When k equal to 2, the curve becomes the polygon segment themselves, right? Here only it won't change, so that would be a linear. A second degree curve is always tangent to the midpoint of all the internal polygon segment. If you see this figure, you can see that this is not the case of for other degrees. If k equals the number of control points, the k equals the number of control points, that is n plus 1. N is control point minus 1, right? Number of control points minus 1 is nothing but n. So here the k is equal to the number of control points, that is n plus 1. Then the resulting B-spline, then the resulting B-spline becomes a Bezier curve. You can see here in this figure, if it is equal, k is equal to the number of control points, that is Bezier curve becomes a B-spline curve, or B-spline curve becomes a Bezier curve, because there is equal, k is order and the is equal to number of points, so there is no any change in the curve. So if you see the multiple control points induce regions of high curvature of the B-spline curve. The multiple control points induced regions of high curvature. This is high curvature of B-spline curve. This is useful when creating sharp corner in the curve. This effect is equivalent to saying that the curve is pulled more towards a control. Effect is equivalent to saying that the curve is uh, equivalent to more towards control point by increasing its multiplicity, increasing its multiplicity. So another is property is characteristic is increasing the degree of the curve make it more difficult to control and to calculate accurately. Therefore a cubic B-spline is sufficient for a large number of applications as well. Thus, for often the non-periodic B-spline curves have been we discussed now. So the same theory can be extended to cover closed and periodic B-spline curves as well. So next video we'll see the numerical part of uh, Bezier curve and a B-spline curve. Thank you one and all.